Hello, ladies and gentlemen. Want to welcome you to this course of GaussDB Circle Optimization. And upon the completion of this course, you'll be able to understand GaussDB Circle execution mechanism, understand GaussDB Circle execution plans and operators, as well as understand GaussDB Circle optimization policies and the corresponding optimization strategies. So here is the content for this course. We have 4 main sections to go through. We'll start by looking into some circle tuning basics, which includes circle execution mechanism, plan and operator, as well as statistics, GUC parameters, and plan hint. We'll go over each of these in detail, knowing what they are, how they work, and how could we use these to help us optimizing our circle statement. We'll begin with the circle execution mechanism. So if we look at the flowchart on the right-hand side of the screen, we can see a pipeline of execution of the circle statement. And this describes the processes that it will undergo in the database to give out the final result to the user or our application. So first of all, our query would go through lexical and semantic analysis. So the lexical analysis, what I do is it will break down the circle into words and classify the words to generate a syntax parsing tree. So during this analysis, it will check if the incoming circle is grammatically correct. And after this, the syntax parsing tree would be the input for the semantic analysis. Semantic analysis is performed on each lexical unit to ensure the fields involved in the syntax can be correctly identified by the database. So for instance, it would check the table name and the name of the attributes we write in our query. They actually exist in the database. So finally, a query tree is generated. The next step is query optimization. This consists of 2 parts, query rewriting and plan generation. Query rewriting rewrites the query tree based on certain rewriting rules. So for instance, whether a subquery can be put up and optimized as a join operation, or when we have some constant expression like 1 + 1, and that would be replaced by 2. Here is also an example on the screen where t1.column1 is greater than 5 and t1.column1 is greater than 10 would be simplified into t1.column1 greater than 10. And right after the query writing, we have path generation, which generates the efficient plan tree based on the query tree and our cost model. The cost model takes in 2 important factors into consideration, which are the statistics and GUC parameters. With all these information, the cost model would be give the path with the lowest cost to execute the circle. And by lowest cost, I mean the plan with the smallest execution time that the optimizer can think of. And once we have the plan, the execution engine or the executor will execute the circle statement based on the plan tree and interact with the underlying storage engine to get the data it requires, process the data, and return it back to the user. Now we have a big idea on the workflow of the circle execution. We can dive deeper into the details on how the execution engine executes the plan based on the plan tree. We call the smallest units in circle execution operators. And each operator, just as its name suggests, performs a certain operation. And there are 4 types of operators in total in GaussDB. The first type is the scanning operator. What they do is they extract the data from the underlying data sources. It could be a file system or via network. Generally, the scanning nodes or the scanning operators are located at the leaf nodes of the execution tree, meaning they are typically the first operators to be executed. They serve as the data input source for execution. And typical scanning nodes are sequential scan, index scan, and subquery scan. Expression filtering can also be carried out in scanning operators, which is the condition we specified in the where clause. And the second type is the control operator. Control operators do not map any algebraic operations, meaning that they do not carry out any calculations. They are only introduced to the executor to complete some special processes, such as limit, recursive union, and union. They are used to control the data flow. And the third type is materialized operator. They will store the result set or intermediate result set in disk or memory. So when there is an operation in future that would require to access that piece of data, that process could possibly be accelerated because we have fetched these ahead of time and do not need to recompute the result. And typical materialized operators such as sort and aggregation. And one key feature of the materialized operators is that all data needs to be scanned before being returned. So for instance, for the sort operation, we have to scan all the data before we can return the first row. And finally, we have the join operators. They are used to cope with the association operations in database. Operators are classified into merge join, nested loop join, and hash join based on the processing algorithms and data input sources. There is an example on how the operators are interacted uh, and on the left-hand side of the screen. So this is a tree structure where each node in this tree is an operator. And in this chart, the blue arrows denotes the invoking flow. So we can see the union operator invokes merge join and nested loop join, and the two join operators invokes the sort and scan operators. And the green arrows in this chart denotes the direction of the data flow. We see the scan operators give the data to their parent nodes all the way up to the top. And they are at the leaf of the execution tree, and they are at the end of the invoking flow. And they're also the first type of operator being called. So only with the data they provide, other operators can start their work based on their data. From the last slide, we learned that the operators execute the plan. But what about the plan itself? So what information or what input does the optimizer take in order to generate the plan? And in this slide, I will introduce you to the circle statistics that provides the metadata information about objects such as tables, indexes, and columns, and so on. With all these information given to the optimizer, it can start to generate a relatively efficient execution plan for the executor to execute. And here is one simple example for the circle. Select everything from table TT where value column is equal to 5. And how can we determine index scan is better or sequential scan is better for this case? The answer is that if there is a data skew and most value in the value column is 5, we should use sequential scan. Otherwise, we could probably use index scan. So, the statistics is a crucial part in plan generation. And currently, GaussDB collects statistics by periodically analyzing and persisting the statistics to data dictionary. And therefore, statistics are not real time, but you can run analysis statement to forcibly update the statistics. And this leads to a rather interesting following question. So, given that the statistics are always real time, would the execution plan be the optimal one? And the answer to this question is no. This is because even though we have real-time statistics, GaussDB only have a limited time to search for the best path in its solution space. And of course, in theory, we could find out the optimal plan, but that would cause the optimizer to spend too much time to iterate through all possible combination of operators. We do not want a query that takes a little time to execute, but takes a long time to plan. And therefore, this is a trade-off between the planning time and execution time. And GaussDB can only provide the optimal solution within its limited solution space. Now, since the statistics is so important, how can we possibly view them? So we can view these by querying the following system catalogs. For instance, PG classes, PG stats, and so on. Here we provide two examples. We can query PG class to obtain the table statistics and PG stats for column statistics. And on the right half of the screen, there are some key features in the statistics, and they are all attributes from the PG stats table. For instance, the null frac denotes the percentage where this attribute is null, and distinct denotes the number of distinct values in these attributes. Most common vals and most common frequencies determine the most common value appeared in this attribute and its frequency. And the histogram bounds describes the boundaries of equal height histogram. In GaussDB, we use equal height histogram to describe the density of the data. As an example, we can have a look at the histogram on the top right corner of the screen. We see each section has the same height as others, and there are boundaries. For instance, from 1.5 to 2.0 and 2.0 to 2.7, and so on. Each block in this histogram denotes a fixed number of data. So for instance, there are 10 tuples in the first section, and there are also 10 tuples in the second section, and so on. And the blocks with a narrow width would have a higher data density, and the blocks with wide width would have a sparse data density. And the optimizer uses this information from the histogram to determine the data skewness and choose the best operator for different scenarios. And down here we have an example. We create a table TT and we insert some values into it. Then we analyze the table. And now we can select relation name and relation pages from PG classes where relation name is TT to view the statistics on the table. So we can see the table information. And moreover, if we want to view the statistics on the attribute column, we could write something like this. We could view all the key statistics information related to this column. And we can see we have a null frac of 0 because there is no value, no null value for this attribute in this table. And we can see the n distinct is 0.8 because we have 8 distinct values. And we have the most common values is 5 because we have 3, 5 here inserted into the table, and most common frequency is 0.3 because 3 out of 10 is 3, it's 0.3. And we have our histograms represented in this array, and where each number in this array is the boundary for the histogram. So in other words, the histogram have 6 blocks in this case. The first block starts from 1 to 2, and the second block starts from 2 to 6. And we note that 5 is not in the array because it is the most common value. Its information has already been recorded. So I guess enough of the statistics. In this slide, I will introduce the circle execution plan. So circle execution plan is a sequence of steps that the database executes to run circle statement. And the execution plan is the core of the circle performance analysis and tuning. The execution plan displays the following information. The order we use to access tables, the access methods for each table in the circle statement, and the methods for joining the tables, and display information such as filtering, ordering, sorting, and count aggregation. And there are 3 main elements in the execution plan that we should focus on. The first one is the access paths. So basically how we are able to get the data. And the second is join sequence. How should we join the tables? A and B first, then C, or A and C first, then B? In most cases, decisions like that would make a big difference in total execution time. And finally, the join operators. Here we have a simple example of circle execution plan at the bottom of the screen. We can see before the circle statement there is an highlighted explain keyword. So with this keyword, what gets printed on the screen is no longer the result set, but the plan generated by the optimizer. So in this plan, we see there are indentations, and the indentation denotes the depth of the node in the plan tree. Let's have a closer look. We can see at the last line, we have our leaf node, where the database performs a sequential scan on table T2. And the data obtained is then hashed, building a hash table. And the line above that we see at the same layer in the tree, data from T1 is retrieved by sequential scan as well. And that data is probed into the previously built hash table, forming the result of the hash join at the top layer. And with this, and within this query, there are also some information we can look into. For instance, the cost. The cost here is the cost generated by the optimizer based on the cost model. So this circle is not actually executed, but simply the output from the optimizer. And the rows are the estimated rows based on the calculation and the estimations from the statistics. And the width is the width of row in bytes. And in this page, let's have a closer look into the execution plan because it's really important. So if you look at the right-hand side of the screen, you will see a bunch of available options. And these are all the options that we can add after the explain keywords to add or take away some informations. So for instance, we could use explain analyze keyword to actually execute the statement and displays the running time, the running and run explain cost off to get rid of the cost information. And here we have one example on circle execution plan. We see that the scan operators obtain data on T1 via index only scan and sequential scan on T2. The data obtained on T1 is then broadcast to other data node for the nest loop join operation. So whenever we see data node, it is a sign of a distributed plan, where DM processes the data and CN gathers the result. And that's why we would have a stream gather operator on the top. We would introduce more detail on distributed plan operators in the later of this course. In this slide, we introduce the gREC parameters explain perf mode. So if we set it to pretty, we would have the Oracle style performance information printed up. And I'm not going over all the detailed logic of this execution plan, just want to show you some important fields in the execution plan that we should probably focus. So note in this execution plan, we use explain performance prefix, which execute the circle. And that's why we see the columns like A time and A rows, where A stands for the actual, time or rows in this context, and E stands for estimated. And here are a few highlighted parts in this plan I want to focus on. So on line 3, we have a streaming type of local gathering. And the local gather means that we have the job done in parallel. And here the degree of parallelism is 64. And on line 7, we have a hash join operator. And in the brackets, we have 8 and 14. These are the ID of other operators, meaning that the hash join operator is taking result from line 8 and line 14 as the inputs. And the A time have two values in its brackets. The first time and the time, the first is the time for the thread to complete this operation, and the second is the time for the last thread to complete this operation. And if we want to have the total time for the operation, we simply take the difference between the execution time of the operators. And the other thing to notice that here is we need to keep an eye on the A rows and E rows if the difference between them are too large. This means the statistics is inaccurate and we need to update them by analyze the relevant tables. In this page, I'll be introducing some memory configuration parameters in GaussDB. The first is shared buffers, and this parameter specifies the size of the buffer pool to be used by GaussDB, and it is advised to set shared buffers to a value which is less than 40% of the memory, and we can increase or decrease this value based on our scenarios. For instance, for the query at the bottom, we have quite a lot of temp read and write to the disk. And this is because the buffer pool is not large enough to fit all results. And in this case, we have to increase the value of the shared buffers to have a higher hit ratio. And by the way, we can add buffers after the explain keywords to view the buffers information. And the second parameter is workmem. Workmem controls the memory available for operators before writing to disk. In some cases where workmem is too small, data would be written to temporary table spaces and performance could be greatly reduced. For instance, when we are building a hash table and the size of workmem is unable to hold the table, that means part of the table would be spilled to disk, and whenever we need it, we would spend quite a lot of effort to retrieve it from the disk, which could severely affect the performance. And currently, the operators affected by the workmem are hash, AGG solid material, set OP, window AGG, and their vector versions. And apart from the memory parameters, Here are also some GUC parameters we can use to control the operators. So for instance, we could enable and disable a scan operator by set enable whatever the scan is to on or off. And we can do the same thing with the join operators and the distributed execution plan parameters. We'll take a closer look in the distributed plan in the later part of this course. Here are some other ways to affect the execution plan. And in this slide, we will introduce plan hint. Plan hint is a special circle syntax which can be used to manually intervene the selection of circle execution plans. The hint syntax is added to the circle to guide the circle optimizer to select a specific execution plan. We can specify the join sequence, join operator, string, and scan operators, as well as the number of rows to be estimated. And apart from that, we can also use the hint to specify the skew information. Plan hint is used when we know the optimal circle execution plan, or we want to manually stabilize the circle execution plan to optimize the performance. So in other words, we use plan hints given we know more than the optimizer, so that we force the optimizer to generate the plan based on the hint. And when we need to use a plan hint, we can refer to the following example. We write our hint in the form of the comment. And after the plus sign, we first specify the hint we want to give, and then its value. So if we wanted more hints, we just separate them with an empty space, just like this. And please note that we need to put the hint right after the select keywords, otherwise it's not going to work. And in the following example, we want the query plan to carry out the sequential scan on table T1, so that we specify the hint like this. And in the printed query plan, indeed, we have a sequential scan that is being used. Based on our needs, there are quite a lot of hints that we can choose. For instance, the hint specifying the join order, hint on the join operators, hint specifying the number of rows in the result set, and so on. There are also some simple examples given for the scan hint and join hint. We could enable or disable the table scan and index scan by writing our hint in this format. And in the bottom, we could enable or disable the certain join operators by specifying the join hint and the tables. Here we give some more examples. So for instance, we could use the leading keyword to specify the order of the join tables. For instance, we could have 3 tables, T1, T2, and T3. And if we want to join T2 and T3 first and then T1, we could write in this form by putting T2 and T3 in brackets, and the optimizer would know to join these tables first. So just like we are doing algebraic operations, what's inside the bracket goes first. And when we write the hints, there are a few tips that we should keep in mind. The first tip is that we need to make sure the table in the list must exist in the current layer or promoted subquery. In other words, if we specify the hint in the subquery, the hint would only affect the subquery, but not the overall query. And the table in the list must be unique in the current level or promoted subquery. So if the name is not unique, we could use different aliases to distinguish their name. Otherwise, we would confuse the optimizer. And thirdly, a table can only appear once in the list. And finally, if the table has aliases, the table in the list must be using their aliases. We can also use the hint to adjust the number of rows of the intermediate results by using the rows hint, we can use some algebraic operators to change it, like plus minus multiplication, and we can also use this hashtag to specify the estimated number of rows in the result set directly. So for example, we can use hashtag 5 to specify the result set of table as 5 rows, or T1, T2 times 100 to multiply the number of rows output by T1 join T2 by 100. So till this point, we have go through pretty much all the basics on circle tuning. And now we'll be moving on to the next chapter where I will introduce some circle tuning practice and along with some examples. So whenever we encounter a slow circle that we want to optimize, we can follow the following routines. So the first step is to always carry out the explain, analyze, or explain performance on the circle statement to obtain the real query plan and performance information. Now, next we need to look into the query plan and find out the operators with obviously high execution time compared to others. And this is to identify the bottleneck operators. And after this, we need to check the deviation between the actual rows and estimated row in target operator information. We want to see if the statistics is correct. So if it is not, we have to analyze the table. In step 4, we check whether the target operator can be replaced by an operator of the same type. For instance, we could see if we can replace the nest loop join with hash join. In step 5, we can look into the parameter related to memory configuration, see if the work mem is too small such that the data is spilled onto the disk, or we have a low hit ratio on the buffers, in which case we need to enlarge the size of the shared buffer. And apart from these steps, we could check whether we can use SMP to accelerate the process by concurrent execution. From this slide, I'll give some real-life examples on circle optimization to help us better understand the techniques that we have learned. So over here, we have a simple query that select everything from the table, store cells where the column is filtered to be a fixed value. We look at the query plan first. We see the execution time is around 3.6 seconds. Note that the time here is in milliseconds. And we see almost all of its execution time has been spent on sequential scan. So therefore, this sequential scan operator is our bottleneck operator that we should optimize. And if we take a closer look at the A rows, we see that there is only 3,000 rows being returned. And let's look at the rows that is being removed by the filter. We see that it's close to 5 million. So in which case, building an index on this column would be very helpful, as it's having a low selectivity ratio. And that's exactly what we need to do here in the bottom. So we create an index and execute the query again. We see that the scanning operator is now index scan, which only takes 13 seconds. And the total 13 milliseconds, sorry, and the total execution time is minimized to 81 milliseconds. In the following example, we have a case where the selection of connection operators is not correct. By looking at the query plan, we see that the nest loop join operator is taking most of the execution time, and therefore we can try to disable it and let the optimizer choose other join operators instead. And in the lower query plan, after we disable the nest loop join operator, GaussDB uses hash join instead. which is approximately 3 times faster. And in these two examples, we are experiencing what is called as the inaccurate statistics. So if we take a look at the highlighted part of our execution plan, we see there is almost 10 times difference on the rows. That is actually being returned, and the optimizer estimates. And in the bottom example, we see there is a row count that is equal to 1. We need to be especially sensitive to the number 1, because when the statistics is not being collected, the default value for the row count is 1. So that's probably indicates that the statistics is not being collected yet. So it's best to analyze the table first before we continue any further. So here we have the case. We also have the case with accurate statistics. So we have a query that runs for more than 10 minutes. And we can see from the execution plan that the index condition on the status column is new. But when we look at the row estimation, we see the number of rows estimated is 1. So therefore, we can suspect that the statistics is not accurate. And in fact, what we have here is a scenario where a large number of rows with status column with the value new has just been inserted into the table. And that's why we don't have the new appeared anywhere in the most common values or indicated by any statistics. And that's why the reason it's also equal to 1. There is only the default 1 rows that the value is stats value is new in the statistics. So the solution here is obvious. So we need to analyze the table T1, and after the analysis operation, the execution time is reduced to over 100 milliseconds. So therefore, it is always a good practice to manually update the statistics after each large number of insertions, updates, and deletions. And in this page, we have a case where the memory parameter is incorrect. We see there is large disk usage in sort operator, and the solution is to increase the work mem, and the optimized plan uses memory instead. And we see the execution time is optimized from 3.5 seconds to 2.6 seconds. And also, this is also the previous example. And if just in case we want to further optimize the execution time, we could choose to use the SMP features to enable the parallel table scanning, and with a concurrency of 8. So we set query dope to 8, so that we set the concurrency to 8. And as a result, we have decreased the time further from 2.6 seconds to less than a second. So till this point, we have went through all the basics in circle tuning, and I've walked you through with some examples. And in the next chapter, we will be studying distributed circle tuning. And just like before, I will start by introducing the distributed plan and the optimization policies. And after that, we'll dive into to get a bit some we'll dive into some real life examples. So in this slide, I will introduce the execution process for a distributed database system. And the overall process to execute a circle statement can be summarized into 5 steps. So first, the service application sends and circle statements to the coordinator node. And the circle statement can contain the operations of insert, delete, update, or select these operations to the data. And next, the coordinator nodes use the optimizer to generate an execution plan. And from this point on, we will call the coordinator node CN and data node DN as their shorthands. And in distributed database system, CN node is used to receive circle and break down the works to DN. And DN are responsible to store the data and do the calculations and give the result back to CN, where CN summarize the result and give it back to the user or the service application. And in our system, data is evenly distributed on each node using consistent hash technology. And therefore, it would be common that DN might need to obtain data from other DNs during data processing. And GaussDB provides 3 types of stream operators to help the flow of data between these nodes, which are broadcast, gather, and redistribution. Broadcast stream operator broadcasts the data from one node to all other nodes, and gather stream operator gathers the data from all other nodes to one node, often used by CN to collect the overall results from DN. And the redistribution redistributes the data between the nodes. For instance, D1 might need some data from DN3 to carry out its join, in which case that piece of data would be transferred from DN3 to DN1 via redistribution stream operator. And going back to our pipeline, where when the DNs finished processing the data, it would return the result set to CN for summarization, and CN sends the summarized result back to the server application. And the overall cost to execute a query in distributed database system consists of 3 main parts, which are CPU, I/O, and network. And the advantage for the distributed execution process is quite obvious. If we look at the chart on the right-hand side of the screen, we can see whenever the system is processing a query, it can be accelerated by using the parallelism between the nodes. And this is each DN takes in part of the work. And apart from that, the process could be further accelerated via the parallelism within the nodes by enabling multi-threaded parallel execution. We have mentioned the previous slide in the previous slide that the data are distributed between the nodes, but how are they divided? So in GaussDB, the tables are divided horizontally into distributed clusters, and that is each DN would have a part of its tuples from the table, and when we need to retrieve or transmit the data, GaussDB uses its parallel data processing technology to quickly locate the data storage location. And in GaussDB, we have 4 types of data redistribution mode. The first one is replication. This is used when the size of the table is small. Replication copies the full table data to each DN. The second is hash. When we create a table, we can specify the distributed by hash keyword. It's just like here, showing in the bottom. We also specify the distribution columns to compute the hash values. And the data are divided into DNs by their hash values. And the third mode is list, where the data is distributed into specified DNs in list mode. For example, we have a table of citizens, and we could use the name of the cities to distinguish which DN they would need to go. And finally, we can divide the table by range. Say we divide the citizens by their age, like for all the citizens with age lower than 25, they go to DN, and between 25 and 50, they go to DN2, and so on. And on the right-hand side of the screen, there is a chart showing the four modes of data distribution with replication, have a copy of the table, of the full copy of the table on each DNs. And for hash, range, and list, the data is mapped to the DNs with the rules we have just described here. And knowing we could divide the data with certain rules, it is important for us to use the correct way to distribute them. And in this slide, I want to introduce some rules where we need to comply when selecting a distribution column. So first, we need to make sure that the data can be evenly spread into the DN, such that no DN would have more pressure on data storage. So for example, we can select the primary key as the distribution column of the table. Say we select the ID card number as the distribution column in the personnel information table. And if the first rule is met, we do not want to select a column with a constant filter. So for example, for the query, select everything from student, where age is equal to 25. We should not pick age as the distribution column, because whenever we run this query, we would have all the age equals to 25 in one DN, and therefore what happens is that one single DN does all the work while all other DN stays idle. And this is a case where we have a calculation skew. And if the first two principles are met, it is best to select the column from the join condition in the query as the distribution column, so that the join task can be pushed down to the DNs for execution, and the communication data volume between the DNs can be reduced. And this could efficiently reduce the cost of data redistribution. In GaussDB, we have three types of distributed plans. The first one is remote FQS query, where FQS stands for fast query shipping. Its execution principle is that each DN generates a plan based on the pushdown statement, and the execution results are summarized in the CN. So in this scenario, no data is exchanged between DNs during the execution. Let's refer to the chart on the right-hand side of the screen. When there is a circle coming in, it went through circle parsing and semantic analysis on CN. And the next step comes the distributed plan selection. When it selects the remote FQS query, the previous analysis would be inversed. So, and what the DN gets in this case is just the original circle sentence. The DN would have to go through all the process of circle parsing, semantic analysis, plan generation, and execution. And in this case, DN does all the heavy lifting job, whereas CN is just responsible for dispatching the circle to DN and collect the final result. This plan maximizes the advantage of parallelism between the DNs, and hence we say it's the most efficient one. And the second plan is string plan, where the CN delivers the circle execution plan to DNs. DN receive the plan and execute the plan, and give the result back to the CN. These scenarios would involve data exchange between the DNs, and therefore this does have some extra network cost. But still, in this plan, DN does most of the work. And the third plan is remote query plan, which delivers some circle statements to DN. And when the DN completes the execution, CN collects the result and carry out the rest of the execution. And this is bad because CN handles a significant part of the workload on calculation. And we use this plan when the first two generation conditions are not met. And in the following slides, we will use examples to introduce each of these plans in more detail. So let's look at the first mode in more detail. So the scenario is here, a statement can be completely pushed down to multiple DNs for execution, and the data interaction is not required between the DNs. And the CN directly generates a remote query plan without going through the optimizers and delivers the plan to DN through the executor logic. And each DN generates the execution plan based on the pushdown statement and executes the plan. And the execution result is summarized to CN. So in the following example, we have a system with one CN and two DNs. And our circle statement is select everything from T1, T2, where T1.column1 is equal to T2.column1. And we have our two tables, T1, T2, distributed by hash. With the same column 1. That means all the tuples with the same column 1 values would fall into the same DN, and since from our circle statement we are joining based on the column 1's value, it is easy to see that the DN has all the data it requires to carry out the join operation. And there is no data exchange between the DNs. So in this case, each DN can safely execute its original circle statement without any risk. And the CN is simply the dispatcher of the circle and the collector of the final result. And the second mode, where CN delivers the execution plan to DNs. So again, let's go through the scenario and principle. So this is where data need to be exchanged between the DNs, and CN uses the optimizer to generate the execution plan with the string operator based on the original circle statements and delivers the plan to DN for the execution. And data interaction exists during DN execution. The stream operator establishes a connection between the DNs for data exchange, and CN receives the result and summarizes the result. And still, DN takes on most of the calculations. And similar to the last example, we can have our join conditions on column 1 for both tables. However, what's different here is the distribution column. We see that the table T1 is distributed by column 1 and T2 is distributed by column 2. And since we see here the join key and the distribution key, they are not identical. That means one DN cannot complete the join operation completely on its own. So it would require the data from other DNs to complete the join. And that's why we have the data from T2 that is being transmitted to DN1 by the stream type redistribute. So, and in this case, CN is still the dispatcher and collector of the circle, and the data nodes takes the most of this work, but it's less efficient than the previous case because the network cost of the transmitting the data. The final mode in this case is where CN delivers some circle statements to the DNs. And this is the extreme case where the preceding two scenarios cannot be met. So this could be due to recursive statements, tableless queries, complex aggregation operation, etc. The performance is poor. And the CN uses the optimizer to generate a remote query plan based on the part of the original statements that delivers each remote query plan to the DN, and after the DN executes the plan, the DN sends the intermediate result data back to the CN, and CN execute the remaining execution plan after collecting the result data. And CN does most of the calculations. So below here is also an example. And we have a count distinct column 2 operation. In this case, we see that we see the circle DN receives is simply scan table T3 and sends all the data back to the CN. And it is CN that does all the heavy work for computing the distinct values and do the aggregation, which is very inefficient. Now we have studied all the fundamental backgrounds related to distributed circle tuning. And just like before, we would have to dive into some circle tuning practices and real-life examples. So these slides give the routine steps for us to follow for distributed plans. So just like before, the first step is to always get the execution plan, and the step 2 to locate the bottleneck operator. And in step 3, we can consider what is our plan mode. We want to optimize towards the fastest remoted fast query shipping and reduce the number of CN calculations and the data interactions between the DNs. And step 4 is to check whether data skew exists. If so, we might need to change the distribution column to avoid it. And steps 5 to 8, they are all the same as previous routine. Basically, we check the statistics, check whether the target operator can be replaced, check the memory parameters to see if we can use SMP to further accelerate the process. So here we provide some examples. The first of which is related to operator pushdown. Here we have a user-defined function which simplify we have a user-defined function which just adds two numbers and return them. And from our execution plan, we see the keyword remote table query here, and meaning that it is the worst situation among the three distributed plans. Basically, the data nodes add the values, but they do not carry out any sorting operation, and the sorting is completely done by the CN. The reason behind this is the sort operate is not pushed down because the function we defined here is volatile. So whenever we define a function in GaussDB, the function is assumed to be volatile, meaning the optimizer is unsure that if we provide the same input to the function, would it actually give the same output? So due to its volatile characteristic, it is unable to do sortings in DN. So unless we assure the function is not volatile by simply add an immutable keyword after the definition of the function. So the optimized version we can see here is also carries sort. It also carries sort operations in DN, and the result given back to the CN is ordered. So CN in this case only need to merge sort the intermediate result set, which is a lot more faster than sorting a completely random set. And the other example here is a case where we can boost the performance by reducing the data redistribution. So here we have two tables, both with distributed column 1, and but the actual circle has a join condition of column 1 equals to column 2. So in this case, we see there is the redistribute stream operator over here, which involves some network cost. So in order to avoid this, we can change the distribution column to T1 to T2 to column 2 over here, and therefore the plan is upgraded to remote FQS query, where we have no data change between the DNs. And the other approach, which is also possible, is to use the replication table, so we can get all the information when carry out the join, but we need to make sure the table does not contain a large number of data, and its change is infrequent. Now I want to talk about one important phenomenon in distributed system, that is data skew. Data skew refers to the uneven distribution of data between the DNs. This would make the nodes of the MPP structure unequal, resulting in one node stores or calculates much more data compared to other nodes. Data skew includes storage skew and calculation skew. Storage skew severely limits the system capacity. The system capacity could be limited due to a skew of a single node. And calculation skew severely affects the system's performance. And the skew node needs to process a much larger amount of data than other nodes. And as a result, the skew node reduces the overall system performance. Data skew could also severely affect the scalability of the MPP structure. Data with the same value is usually stored on the same node during the storage or computing, and therefore, even if the number of nodes is added, the system capacity is still limited by the skew node. So other DNs have to wait until that skewed DN finishes work so that they can all continue. For the storage skew, data is stored in DN, and we can improve the efficiency through distributed execution. However, if the data skew exists, some DNs will become bottlenecks in distributed execution, just like we described in the last slides, which could affect the query performance. So the problem is usually caused by improper selection of distribution columns. We can always adjust the distribution columns to reduce data skew. And for the calculation skew, it happens sometimes when the data is initially evenly distributed but during the execution, operator redistribute the data during the query execution, which may cause the data skew and the corresponding calculation skew. And calculation skew is more difficult to identify and tune in advance than storage skew. And GaussDB introduces the runtime load balance technology, shorthand for RLBT solution. That is, by identifying the statistics and rules, GaussDB automatically solves many computing skew problems. And in addition, GaussDB provides skew hints to manually solve some computing skew problems. Here we give an example related to data skew. We have a slow query like this, and we have checked the data size on each node. We found out DN2 contains more data than other nodes. We can check this by using the skewness function to have an overview on data distribution. So what we do here is to change the distribution columns on table T1 so that the data is more evenly distributed. And as a result, the time is improved from 1.6 seconds to less than a second. So that is pretty much all the content we have today. So in today's course, we learned the main concepts of circle tuning, the tuning tools, and how to use these tools. We have went through the basics for circle tuning, starting from the circle execution mechanism. We introduced the principles and components of the execution plan, including the 4 types of operators in execution plan, and what they are and how to choose them. And by introducing the statistics views and in both databases, you can understand the composition of statistics and its impact on plan generation. We have learned 2 very useful tuning tools, GUC parameters and plan hints, and also the way to use them. And for distributed system, we explore the generation conditions and execution steps of the 3 types of distributed plans, and I introduced the 4 data distribution modes supported by GaussDB and how to optimize distributed plans. Here we have some multiple choice questions we can practice on. So the first question, can the plan hint takes effect anywhere in the circle statement? The answer is false. And we have to put the hint right after the select keyword and also assure it to be in the right correct layer. And second question, data skew indicates the amount of data stored or calculated on the node is much greater than on other nodes. So true, that is correct. Question 3, how can I set the GUC parameter to increase the sequential scan cost of to disable the sequential scan? The answer is C. So if we think a little bit more beyond the scope of this function, what will happen if we set every scan operator to be off? Will the query still execute? And the answer is that the query will still execute. And the set whatever scan to be off just simply add a large penalty cost to use this operator. But if we set everyone to off, that means if we set every operator to be off, that simply just means the optimizer can still choose an operator despite their cost is or large. So to still choose a relatively small operator to execute. And final question, which of the following optimization methods can be used during circle tuning? A operator parameter optimization, that is by setting the GUC parameters, plan hint optimization, memory parameter optimization, and SMP optimization. And the answer is all 4 of these. We could use all of these to help us tune our circle statement. Yeah. And I guess that's all the content I have to deliver for today's course. And I thank you for listening.